maybe some things that are maybe obvious if you looked at them. If you have two functions that are continuous, sort of like the limits, you know that when we looked at limits, we said if you have two different functions and you know the limit at a certain value, you know the limit of their sum, right? When we had before, we had if you have one function here, another function here, you know the limit of this one is m and the limit of this one is L. If that's f and that's g, if you know the limit of both of them, then if you graph f of x plus g of x, the limit is just going to be the sum of those two numbers, L plus m. It's sort of that sort of rolls over into this. If you know that two functions are continuous at a certain point, then all these different combinations are also continuous. They have to be continuous. So if you have two functions that are both continuous, when you add them together, it's going to make a continuous function. All that means is if you take something like x squared and x cubed plus 2, both of those are continuous. So if you take x squared and x cubed plus 2, if you take those two functions separately and then you add them together, whatever it's going to be some other function up here, okay? But whatever it is, who knows? I don't know what it looks like. Going down again, I guess. But whatever it looks like, it's going to be x cubed plus 2 plus x squared. That function's also going to be continuous. It's not suddenly going to have a big jump in it here like this, right? If you have two things that are continuous, you add them together, the new one's continuous. If you subtract them, it's continuous. If you multiply them, constant multiple, you divide them. Of course, that's true, right? As long as the value is not one of those undefined values, okay, then you're okay. Every polynomial is continuous for that reason. Any polynomial you make up, x cubed plus whatever, you make up any numbers you want here in front of terms and you put it on your calculator, it's going to be continuous. Every polynomial is continuous. Every rational function is continuous. If you put a polynomial on top, x cubed plus some stuff and then something else on the bottom, every one of those is going to be continuous because anywhere it's the only place that discontinuities are going to occur, it's not defined there. So it's continuous at every point on its domain. The composition of functions is continuous. This one's harder to say because, if f is some continuous function at c, okay, and g is continuous at whatever that y value is, right? If you have some value like 3, okay, x equals 3, and you know that you have a function that's continuous there, okay, that chain is also going to be continuous. You could pick square root of x and, 2 times x plus 3. If you combine those together and you put this function in there, you make a composition of those functions. 2 square root of x plus 3. Since you know the square root function is continuous, and you know this function is continuous for every single value, this has to be continuous. Anyways, I put this one in here, but I don't know how useful this is. It's a big weird combination of a bunch of things, all of which are continuous, right? Absolute value of something. If you look at the graph, you'll see it's continuous. If you want to kind of argue algebraically that it's continuous, you got to start by saying absolute value function is continuous, and this is the product of two continuous functions, so it's continuous. And this is the sum of two continuous functions, so it's continuous. And then you got a quotient of two things that are continuous, so that means it's continuous, and then a composition, absolute value of something continuous, is continuous. That's kind of all that needs to be said here for that, I think. If you looked at the graph, you would see that. Okay. Last thing we're going to talk about is this intermediate value theorem, which is a pretty important idea. It's sort of obvious when you think about it, but when we write out what it means here. Okay. All the intermediate value theorem What does intermediate mean? What does that word mean? You call kids who are in grades 4 to 7 intermediates. You call younger kids primaries, and you guys are secondaries. What are intermediates? Middle, right in the middle. If you have some kind of a graph, and you know that at A it's this value, I'm going to call it f of A, some function, right? And you have another value over here, B, and you know it's some other value, f of B. It could be numbers. Like if you want to start with numbers to get this, if this is 2 and this is 5, and at 2 this thing is 3, and at 5 this thing is 7, something like that. Actually, let's make it bigger numbers so we don't get them mixed up. If this is continuous, okay, if f of x is continuous, if these are 2 points on a function that's continuous on this interval, if we know it's continuous on that interval, then f has to hit every value in between here. If you know the function that joins those 2 points is continuous, it has to take on every value in there at least once, right? There's no way for me to draw a line from here to here without hitting every one of the y values in here. It's sort of geometrically obvious when you try to draw it, right? I can't draw a line the only way to miss some of the values here is if I stop and make a break like that, right? Oops, missed the point at the end. No matter how you draw the line in between there, no matter how the function goes, even if it goes down first and back up like this, I've hit all the values in here. Every single value in there has been hit at some point, right? If right now the temperature outside is, what is it outside now? Let's say 20 degrees. And we know later on tonight it's going to be 7 degrees. And we know that it's continuous because temperature changes continuously. It doesn't instantly change from one thing to the other. We know that the function that joins those 2 points is continuous. All that means is it has to take on, the temperature will at some point be every single one of those things, right? You get in your car and you start out at 0 kilometers an hour, and at some point you're going 100 kilometers an hour. If we know that, if you draw a graph of that, here's 0, you're going 0. Here's however much later, 30 seconds later, you're going 100 kilometers an hour. So we got a point up there. If we know that the speed of your car is, this is continuous, right? This is speed, right? If we know that the speed of your car is continuous, right? The speedometer doesn't just suddenly instantly jump. At some point in there, you've been going every other speed between 0 and 100, right? You start at 0, you get to 100. You don't skip over, the speeds from 50 to 70, right? It doesn't suddenly miss those. If you know that the function's continuous, it has to hit all those values. That's all that this intermediate value thing is. So if you draw some kind of a function here, okay, all that this is saying is if, we can write it out right now actually, make some space over here. If f of x on the interval a, b, okay, they use that kind of notation. If you don't like that, then you can put in something instead, x less than b and greater than a, okay? Whichever way you prefer to write that interval. Then f of x must take on every y value in between there, right? Must take on between f of a and f of b at some point, right? Okay, that's all that's saying. I can't remember why I made this the way I did, but I guess because this is down here, yeah. If this is discontinuous here, right? This function is obviously discontinuous from -3 to what interval? You pick any interval you want across this thing here. From -3 to 2 or 1 or something like that. It's not continuous. So if I move this now, the red line is, it's taking on every value down to about 2, right? It's covering all these y values, but then as I go down this way, it's suddenly gonna jump down to there, right? It missed all these values. In your mind, you might have seen it as jumping, right? But it's instantly flipping from there to there, right? Your mind is perceiving that the line's moving up there, but it's going there. It never hit any of those values in there, right? All the intermediate value theorem is saying is, if the function's continuous, so if I join this together here now, that's the only way to ensure that it covers every one of the values, right? From here, -2, it's going to cover everything from -2 up to 5 or whatever as I go across here. Okay, again, it's sort of geometrically obvious. It covers every single value. It may cover every single value even if it's not continuous. Like if I do that, it's not an if and only if thing. Even with the little break in it there, it may well cover every value, which it does because it jumps up and then comes back down. But the only way to ensure that is if you know for sure that it's continuous, then it has to take on that. Right? It has to take on every value at some point, being continuous like that. Okay? That's all that this intermediate value thing is saying. If it is not, if you got this piece up here, it's going to miss some things, right? And again, most real world things don't do that where there's a big jump like that, right? Your bank balance is something where it's not continuous and it doesn't hit every value, right? If your bank balance starts at, well, I guess we'll start with some money here, $1,000. You wait, you get paid some interest. Right, on your account, it suddenly is 1,050. Did it ever have the value of 1,025? Did you ever have $1,025 in your bank? No, you just suddenly jumped from one to the other. But if this was instead like filling something up with liters of water, it would go like this. If this is continuous, right, as you're filling up the water, it hit every one of those values at some point, right? If you take an empty cup and fill it up with water, at some point it was at every height in the whole cup. That's what this is saying. Okay? The question that's here, this is one out of that textbook, is any real number exactly one less than its cube? You can find it pretty easily, but if you want to make an argument to does it exist, you could use this idea. Exactly, is any real number exactly one less than its cubed? So if you have x and you say exactly one less, so one less than its cube means if I subtract it from its cube, what does that equal? 1, right? If you use this function, f of x equals x cubed minus x, if you have a few values where you know, so without even going to the calculator, we can do this. We can say f at 2, because I think that's probably going to work for us. What's f at 2? What's the function value at 2? It's 6, right? 2 cubed minus 2 is 6. And f at 1, what's f at 1? 0, right? And what do we know about this? What do we know about that function? It's a polynomial. It is a continuous. This is continuous, right? If you're a lawyer, you can appreciate this kind of thing. These are enough facts to answer that question without going to your calculator. These are the 3 facts you need. You need to know the function's continuous, and you need to know 2 values. If I know it's at 1.6 and at one point it's 0, what must be true somewhere in between there? Like I'm just going to put f of c. At some point, what does it have to be? At some point, it has to be 1. There has to be a point where it's 1 because it's continuous. This function is continuous. Like, if you look at it on a graph, at 1 it's 0, at 2 it's 6. However it looks, we know it's continuous. At some point, it has to be 1, right? 0, 6. There has to be a point when it hits 1. So that's enough to say yes, okay?